Hello everybody and welcome to the latest edition of the Physics Corner, a series of videos in which we set up and solve introductory physics problems. I'm your host, Dr. Christopher Sorolla. Today we're taking a look at a simple harmonic motion problem. Specifically, we're going to be given a spring and a mass. We'll take that mass, hang it off of the spring, and give it a starting motion, if you will, by pulling it upwards and releasing it. And our question or questions are to write equations of motion for the system. And while we're at it, solve for any constants of the motion, or at least determine what they are. So let's go ahead and begin. So imagine we have the following situation. We are hanging a spring vertically with a mass on it attached to it like that. And let's allow it to come to a complete rest. So it's just sitting still here, and that's going to be our equilibrium position. Once it's sitting at equilibrium and it's steady, then we're going to lift the mass upwards 5 centimeters and release it from rest. So what do we have for this particular situation? We have a mass given to us is 100 grams. We might as well go ahead and write that as 0.1 kilograms right away. Going to need to do that. The spring constant is also a given at 10 newtons per meter. And we lift it up by 5 centimeters and release it from rest. As long as we aren't touching it, this is simple harmonic motion, that's going to be the maximum distance the mass will ever get from equilibrium, which by definition is the amplitude. And we can write the amplitude as 5 centimeters. Now, we could write the amplitude as 0.05 meters, and that might in fact come in as a handy idea to talk about later. But for now, I'm going to leave it at 5 centimeters. Okay. Now, notice that while we do have gravity involved here, I mean, gravity is what's pulling the mass down, it turns out it's not necessary for solving the system. Okay. That's already been incorporated. Once we went ahead and allowed this to come to rest here at equilibrium, gravity's already involved or embedded inside, if you will, and we don't need to use mg or any other version of g, if you will, to solve for this. So that's not necessary. All right, what do we not know? Okay, well, one of the major ideas that physics people like to talk about is something called the angular frequency here, and that will be the letter omega, so we don't know what that is yet. We also don't know the period of the motion or just the frequency of the motion like that. And we will determine the phase angle of this, or the phase constant, if you will, for this, but I'm going to leave that be for the moment. Okay, so the next thing to do or to talk about is what is an equation of motion for this kind of situation. So earlier in this class, you talked about equations of linear motion. For example, delta x equals v naught t plus 1/2 at squared, and other similar equations like that. Those are equations specifically for a case where acceleration is constant. That is not the case anymore. That's not happening here. So if we craft equations of motion, we have to realize that acceleration is not constant. But if acceleration is constant, then are other things constant? And how do we write equations to explain or to depict how the object will move back and forth? So to cut this story short, when we lift it up like this, we're going to assume we're going to use a cosine function. Why cosine function? Cosine reaches a maximum at 0 degrees. And then, of course, it drops down to 0 after you go 90 degrees of travel. It goes to a negative value. Then it comes back up to 0. Then it goes back up to its maximum and repeats the cycle. If you look at this situation here, I've raised up my mass up to a maximum distance, and as the object is going to move, it'll bounce back and forth like this, but it's starting at a maximum at time 0, or beginning of the phase, if you will, 0. So that makes it easiest to use cosine, which is another way of saying this. The position of the mass as a function of time, and I'm going to call this position x. Let's have positive x going up like that, just to make it clear. That will be equal to the amplitude multiplied by the cosine of omega t plus phi, like that. Now, by the way, this phi here is our phase constant. That depends sometimes on the version of the textbook that you use. There's not a set standard for everybody to use. So I'll use this one, but it could be different for your individual textbook. Don't worry about that too much. And in this particular case, because we're going to set it as cosine to start with, we're going to make the phase constant 0 to begin. So when we actually apply the equation, we don't have a phase constant in there. Now, if this is the case, if we have this equation, then the velocity equation turns out to look like this. It's a negative omega a sine of omega t plus phi, like that. And the acceleration equation will look like this, a negative omega squared a cosine of omega t plus phi. So these equations are ways to express simple harmonic motion. And again, I've chosen this version of them. You may have slightly different versions again in your textbook, depending. But I've chosen this version so that we have a starting point of a phase angle of 0 by lifting the mass up and releasing from rest. Then all these equations work out exactly as they're depicted. You can sometimes see these as sines replacing the cosines. You might see that in your textbook, or your instructor do that for you, or even in lab. Those are usually for convenience. I will point out this, no matter how else you see it, if you have a cosine here for x, you'll have a sine for a v and a cosine for a. If you have a sine for the x equation, then this will be a cosine and this will be a sine. Also, assuming that x is a constant, or excuse me, is a positive, and that's almost always a guarantee this will be a positive, then both of these will have negative signs in front of them. So regardless of what specific versions you might encounter, they're going to have these general properties. Right. So I'm invested in this one, so I'm going to use this. All right, so what I need to do to solve this, I need the amplitude, I need the phase angle, and I need the angular frequency. So out of these three items, I have two of them already. So let's see about solving for the angular frequency. Now, angular frequency is related to the things we have available by this equation here. It's the square root of the spring constant divided by the mass. That is the spring constant of the spring divided by the mass that's hanging off of it. Now also, by the way, we are going to assume, for simplicity's sake, that the mass of the spring is negligible, that it's not going to come into this, and that works out to be a very good assumption under most of these sorts of problems. So we can get away with that. All right, so let's go ahead and calculate. So spring constant was 10 newtons per meter. The mass, and this is why we need to worry about kilograms sometimes, but in standard units, 0.1 kilograms, right? 10 divided by 0.1 is 100. Square root of 100 is 10, notice, all right? And I get number 10. You've probably already learned this by now. The units for angular frequency are the same as the units were for angular velocity, which is to say radians per second. So there is my answer for that. And that means what? I can go ahead and already write down my first equation. My first equation looks like this. Now, the x is the dependent variable, right? That's what we're trying to find. T is the independent variable, but they're both variables, right? They're both variables. So to write the equation, leave the x and the t where they're at. Don't put in numbers for them. We don't have numbers. Put in numbers for the others, what we call the constants of the motion. Amplitude is a constant, so 5 centimeters, all right? Now, sometimes people will bracket that off to make it real obvious. Let's do that. Then it's cosine of, now what's omega? Omega is 10 radians per second, like that, multiplied by t for time. Again, I'm leaving t alone here because that's a variable. So this is where a lot of students get confused. They keep thinking, oh, I must have some number. What do I put in for time? You're not putting anything for time in at this stage. Now, if we asked a question like, given this particular equation, can you then find the position of the mass? Then you would go ahead, put that time in and calculate. We're not asking that. When we ask for an equation, we want the variable still there. Okay, we already said phase angle is 0, so I don't have to write that at all. And that is the first of your equations of motion. So there we go. All right, so I'll leave some space here to write the other equations of motion, but what else do we have? Okay, so I asked, what will be this? Now, a couple of ways to go about this. I could just simply have omega times a out in front, but I want you to notice something also about this. If you look carefully in this equation, right over here, this piece of material, if you will, these two things together, looks an awful lot like an amplitude. And it is, except it's a velocity amplitude. It's an amplitude for how fast it's going, not an amplitude in terms of, say, position, but an amplitude in terms of speed. And that, in fact, another way to think of that, that turns out to be the maximum speed. Just like amplitude, capital A amplitude, is the maximum distance, omega multiplied by A is the maximum velocity. So V max is equal to omega A. Might as well go ahead and multiply those out. So 10 radians per second for omega. A is 5 centimeters, like that. 5 times 10 is 50. Now, because we're taking this repetitive behavior of omega and translating that or turning it back into a linear behavior, like speed, the radians do not come along. They stay away, but we have centimeters per second. So you could write it as 50 centimeters per second, or, if you prefer your standard units, 0.5 meters per second. Right. What does that do to our equation? Our velocity equation then is a negative 0.50 meters per second, and then sign of the same thing in the argument here, inside the parentheses like this. That hasn't changed, right? It's still omega t. And again, phi is 0, so that's why I don't have it. So that's the second of our equations of motion. Similarly, same kind of argument, take a look at the amplitude equation. Omega squared times a is the maximum acceleration. Same argument. So maximum acceleration, so omega squared a like this, that's 10 radians per second quantity squared, multiplied by 5 centimeters. 10 squared is 100, times 5 is 500, so 500 centimeters per second squared, if you will, again, dropping the radians because we're going to a linear quantity. Or, and this would be a little bit more preferable, 5 meters per second squared like that. And that turns the acceleration equation into this. So a negative 5 meters per second squared. And now it's the cosine again. In exactly same fashion, same arguments, and so on and so forth. So there they are. Those are equations of motion for this particular circumstance, right? Again, when you are asked to write an equation of any kind, mind you, you take the numbers that you have, the constants or the values that you have, those can be put in, but you leave the variables alone. So in this case, t and x, and also v and a in this case, all these letters stand for variables. Now, if I have a certain time that I'm given, say, oh, find the values when the time is 5 seconds, I would simply put in the number 5 in these positions here, calculate this interior, take the cosine of that, and so on and so forth to get my answers for these three things. Okay. But if you're just asked for an equation, I don't have to do that. I simply do what I've done already. All right. So last thing to say is the question was, let's determine all the constants of the motion. So what did we have given to us? Well, we had the amplitude and the phase angle. Those are already given. And we decided, or we determined, the value of the angular frequency, omega, as 10. What about the others? Let's take a very quick look at those. So, other possible ways to describe this system are through period and frequency. So, period is related to angular frequency by this little formula here. And that's, yes, that's 2 pi. That's our familiar friend pi is a number. It's 10 radians per second there. 2 times pi is about 6.3, rounded off a little bit. Divided by 10 is 0.63, and that will be seconds. Okay. Time doesn't have a radians part ever in it, so it's always just seconds like that. The last possible constant of the motion was frequency. You could do frequency of 1 of 2 ways. You can either have it as 1 over time, period, specifically, or it could be omega over 2 pi, and I'll write it that way since that's what I started off with. So the 10 radians per second divided by 2 pi like that. And again, rounding off a little bit, that'll be 1.6. Units for frequency are cycles per second, or oscillations per second, if you will. And in physics, we abbreviate that to something called the hertz, which is abbreviated Hz. And that's what you have there. So, one last thing as an aside. Let's suppose we wanted to recast our equations of motion in period or frequency terms rather than what we've got it written. So let's rewrite our position formula here. So we have the 5 centimeters and cosine of 10 radians per second multiplied by t, like that. Suppose we wanted to rewrite this in terms of, say, the period. How do we go about doing that? All right. Well, period and omega are related this way. If period is this, then omega is 2 pi over period, like that, isn't it? So we could rewrite the equation like this. Our 5 centimeters would stay out in front. We still have the cosine. Now, instead of 10 here, we have 2 pi over t. So it would be 2 pi divided by 0.63 seconds, like that, multiplied by time, okay, like that. Or, if we decide to rewrite as frequency, looking at how frequency is related to angular frequency is 2 pi times frequency, like this. So we could also rewrite it as 5 centimeters multiplied by cosine of 2 pi 1.6 hertz t, like that. And all three of these versions are equivalent. So, several comments to make quick before we leave today. First, why 3 different versions? Why don't we just stick with one thing? Well, it depends on circumstances. I find for classes, for example, the concept of period is actually, to my mind, the simplest thing to get across. To simply note how much time it takes for, say, the mass to bounce back and forth. That's a period. That's an easy concept. Frequency is the rate at which that happens, and angular frequency is a even more complicated version of that. Period is the simplest thing to kind of consider. So that's good to do. But if you notice, if I write the equation in terms of period, it looks like that, which is kind of messy. So angular frequency is a little bit more convenient to write rather than period straight up. As far as frequency is concerned, again, same kind of notions for frequency. Frequency, in my mind, is a little bit easier to understand than angular frequency, and you can rewrite it like that. But again, if you write your equation, notice it looks like this, which is a little bit more complicated looking rather than that. And so typically what physics people do is write their equations using omega. Omega is a little bit easier to write. And a couple other things for physics people, primarily, it's a lot easier to deal with in higher level math. When you get up to more and more complicated ways of describing how springs operate, when you start bringing in other things that are not simple harmonic motion, such as damping or forced oscillations, omega is a lot easier to deal with at that level than, say, period and frequency. It's a little bit easier to manipulate, if you will. And so the physics folks tend to use omega or prefer using omega. But they're all correct, right? If you have one, you have all of them. Okay. So, interestingly enough, then, there are potentially, if you want to list them out this way, 5 separate constants of this motion. There's amplitude, phase angle, then there's also angular frequency, period, frequency. Out of that group, only 3 of them are independent of each other. So angular frequency, period, and frequency are all interrelated. If you have one of those, you have all of them. Notice, though, that phase angle is simply the starting point, if you will. So that isn't affected by any of the others. And the amplitude is the maximum distance by which your spring will either stretch or compress. And again, that's not affected by, say, the angular frequency or any of those. They're independent of each other. So that's why it's written and it works that way. But again, long story short over here, if we're talking about writing an equation of motion or a series of equations of motion, it might look something like this. And this is why. All right, everybody. Technical assistance is always provided by Cindy Geltraw and Sophia Turner. Funding comes from the University of Mississippi and University of Southern Mississippi. I'm your host, Dr. Christopher Cirola. Thanking everybody for your attention, as always, and clear skies.